To really get a handle on artificial intelligence, I'm talking about everything from self-driving cars to these new creative tools. We've got to go back, way back, to the very beginning. We need to understand the fundamental building block of it all, this simple but brilliant idea called the perceptron. It's really the question that kicked off this whole revolution, isn't it? How on earth do you take a machine, a hunk of metal and wires, and somehow give it the ability to learn, to recognize things, to make a decision? Well, it turns out the answer was surprisingly close to home. That's right. The first pioneers of AI, they looked for their inspiration in the most powerful computer we know of, the human brain. The blueprint for AI wasn't just invented out of thin air. It was discovered right inside our own heads in the form of the biological neuron. So, before we can even think about building an artificial mind, we really have to understand the original, right? Let's take a super quick look at the microscopic processor that's firing away, powering your thoughts right now. A biological neuron is basically a tiny little information processor. You've got the dendrites, which act like antennas, just pulling in signals. Then the cell nucleus, the soma, it's like the CPU. It adds up all those signals. And if that combined signal is strong enough, bam, the axon fires, sending a brand new message out to other neurons. So it's input, process, output. It's a beautiful, elegant system. Okay, so after looking at nature's design, these early researchers asked a really brilliant question. Hey, could we build one of those? Could we create a mathematical model that does the exact same thing? And that's what they did. The whole journey really started back in 1923 with a very simple model of a brain cell. But the huge leap forward, the real game changer, came in 1957. That's when a psychologist named Frank Rosenblatt introduced the perceptron, an algorithm that could actually learn to classify things it saw. This was it. This was the birth of the artificial neuron. And just look at this comparison. On the left, you've got this complex, organic, kind of messy biological neuron. And on the right, you've got its beautifully simple, clean, mathematical translation. We basically took the core idea of nature's design and turned it into this elegant, functional model. Okay, this table makes that translation crystal clear. The dendrites pulling in signals, those just become the inputs in our model. The cell nucleus where all the processing happens, that's our central node. That critical connection point, the synapse, becomes this concept of weights, which basically control how strong a connection is. And finally, the axon that sends the signal out, well, that's our output. Simple as. So that's what a perceptron is. It's really just a simple mouth function that acts like a brain cell. It's the single foundational piece, the atom, if you will, of these huge things we now call artificial neural networks. All right, so we've got the blueprint. We know what it is. But how does this little mathematical neuron actually make a decision? How does it, think? This diagram shows you the whole process, start to finish. And I know it might look a little technical, but trust me, it breaks down into a super logical 4-step journey that takes you from raw information all the way to a final answer. This slide really demystifies the whole thing. First, the perceptron gets its inputs. Second, and this is the most important part, it applies weights. It multiplies each input to decide how important it is. Third, it just adds all those weighted inputs together into one single number. And fourth, it makes a decision based on that number. That's it. Receive, weigh, sum, decide. So what exactly are these weights? Honestly, the easiest way to think about them is like little important styles. If one piece of information is absolutely critical for making a good decision, the perceptron cranks that weight dial way up. If another piece of info is pretty much useless, it turns that dial way down, almost to 0. And this right here is the final step, the moment of truth. After it adds up all the weighted inputs, the activation function makes the final call. It's just a simple threshold. If the total number is above a certain value, the neuron fires and spits out a 1. If it's below that line, it just stays quiet and gives a 0. It's the ultimate go or no-go switch. Okay, so a perceptron can make a decision. That's cool. But that's only half the story. The real magic, the part that changes everything, isn't just making a decision. It's learning how to make the right one. And this is the million-dollar question, right? How does it know how to set those little important styles? How does it figure out which inputs actually matter and which ones are just noise? It learns the same way we do, from its mistakes. Notice the new piece in this diagram? That little error box? That's the secret sauce. It's a feedback loop. When the perceptron gets an answer wrong, it calculates how wrong it was, and it uses that error to go back and adjust its own weights. So here's the crucial part. It doesn't know the right answer at the start. It actually begins with completely random guesses for its weights. Then you show it an example. It makes a prediction. You tell it if it was right or wrong, and if it was wrong, it nudges its weights just a tiny bit in the right direction. It just repeats this process thousands, even millions of times, getting a little less wrong with every single step.
Okay, we've pretty much mastered the single neuron. Now for the grand finale. Let's zoom out and see what happens when you don't just have one of these, but you start connecting them all together. A single perceptron all by itself is actually pretty limited. As you can see on the left, it can only solve really simple problems, things that can be split by a single straight line. But when you start layering them together into a neural network, like on the right, their collective power just explodes. They can learn incredibly complex patterns that a single one could never handle.
This is honestly the best way to think about it. The simple perceptron we've been talking about this whole time, it's a single brick. It's humble, it's functional, but it's limited. But when you combine millions of these bricks in these amazing, complex, layered architectures, well, that's when you can build a cathedral of intelligence. And that really leaves us with one final, kind of mind-blowing question. We've seen how elegant and simple one artificial neuron is. So what happens when you link together not just a few, but hundreds of billions of them, like in the giant AI models of today? Well, you get the world-changing AI that we are all just beginning to understand. The entire complex forest of modern AI, all grown from this one simple seed.